do we have? Yeah. I'd like to invite Andy Bechtolstein up, please. There is Andy. There's Andy. So Andy is going to be talking to us about Moore's Law and networking. For those of you that don't know Andy, he's the Chairman and Chief Development Officer at Arista, but previously he was the Chief System Architect at Sun. And before that was at Cisco for a while and worked on the team that developed the Cat 4K family. He is a master's in computer engineering from Carnegie Mellon and is a member of the National Academy of Engineering. This looks to be a fantastic talk. I'm really looking forward to it. I think that, as Mr. Underwood said 3 nanogs ago, math is hard, but hopefully this makes it a little bit more understandable to us engineer types. Thanks.
So is the question whether the slides work. Well, I want to talk about 3 things this morning. One is the progress that has been made on the semiconductor side, otherwise known as Moore's Law, over the last many years, and how this relates to networking going forward, in particular to the cost performance of networks. The second topic is how one can take this technology to build scalable networks for large cloud web data centers. And third topic is the kind of what's happening on the optics side to make that all cost effective. How do these slides work? Just push the button. Okay. So jumping right in with Moore's Law. Dr. Moore was co-founder of Intel Corporation, but the original prediction he made was actually dates back to 1965, which was I think that was the year the ARPANET was conceived, and this was before I think they even had integrated circuits, but he predicted boldly that the number of transistors per chip would double every year. This was subsequently revised to doubling every 2 years, so the current Moore's Law is twice the transistors every other year. And this has been pretty much true for the last 40 years. Every other year, there's twice as many transistors on these magic chips that drive everything from CPUs to networks. Now, there's an unfortunate kind of thing that happened on the way here, which is networks themselves didn't really increase at the same rate. So the time frame for Ethernet, gigabit Ethernet, which came out in 1999 or 1998, 99, to get to 10 gigabit Ethernet 12 years later was only a factor of 10x in 12 years. And if I look at the cost performance of wider network routers, I would say they maybe improved a factor of 4 over the last 12 years. So this is kind of a gap, and what I want to discuss this morning is how the future doesn't have to look like the past here. Now, going back to the CPUs, this is a chart from Intel Corporation that shows how their CPUs line up perfectly on Moore's Law. The latest Sandy Bridge Romley chip is 2.3 billion transistors, and the Intel 4004 in 1971 was 2,300 transistors. Now, Sandy Bridge was actually shipping early access in 2001. So in the last 40 years, which is 20 times 2 to the 20 essentially, we did see this million-fold increase in transistor count, which is nothing short of amazing. In fact, there hasn't been anything like this in the history of mankind. And the good news is that the silicon roadmap isn't ending here. In fact, there's this institute that works on predicting the process technologies for at least the next 12 years, and at least for the next 12 years, we're going to get another factor of 100 beyond what's even has been done today, which means that CPUs 12 years from now should be 100 times faster, cheaper, whichever way you mention this, whichever way you measure this. And this is true, for logic density, memory density, flash chip densities. So basically, the current, 2 billion transistor chips will be 100+ billion transistors in 2023. Now the roadmap only extends out 12 years. The physicists believe this can actually keep going for at least another 20 years, which should be another factor of 1,000 beyond what we know of today. And the only thing that could kind of happen on the way there is that it does get more and more expensive to put in the factories and to tool up for these new processes every generation. So if the industry runs out of capital to do this, that may slow it down. But from a sort of invention standpoint, people do believe there's no raison getting there. Now, what this means on the system side is it translates primarily to more cores and CPUs. You've seen this with, 10 years ago there was single core chips, and then there was dual core, quad core. Now we have 8 core chips, 16 threads, 16 core coming shortly. The previous slide was a logarithmic slide. This is a little easier to imagine on a linear scale. So again, the current Intel CPU, 8 cores per socket, 16 cores on a 2-socket machine. 2 years from now, that should double to 16 cores a socket. 2 years later, will double again, double again, double again. By 2022, should be 1,000 core chips. So this is how quickly, continuously improving things improve. Now, there's a few things that are not changing as well, which is the memory hierarchy isn't scaling. People are putting in bigger caches, but the latency still applies. So clock rates kind of have suffered here. There's also an issue with power consumption per core. Hard disks, of course, haven't kept up. Flash is coming along just in time to speed up the I/O. One thing about flash is that it's actually the densest kinds of chips available today. People have managed to put 64 gigabits, which is 8 gigabytes on a single die, and then they stack 8 of these dies in a package, which makes it a 64 gigabyte package, which is sort of inside your iPhone or iPad. But the progress here is that in the next year or so, we would expect that to quadruple, and then to quadruple again 4 years later. So the terabyte flash phones or flash chips are just around the corner. But to summarize Moore's law here, the doubling in transistor count has been extremely predictable, and it's expected to continue for at least the next 12 years. And it's a little harder to forecast beyond that, but there's every reason to believe it will continue well beyond that. Now, going back to the question of why networking hasn't kept up. There is one issue here, which is the Moore's law really applies to the area on the device, which is a square effect, right? Every time you shrink the process, you get twice as much shrink transistors in the same area. The number of I/O pins per package, unfortunately, haven't really increased in the last 12 years at least. In other words, we had the same density, the same size packages available in 1999 as today. And the only thing that has improved is, in fact, the I/O coming out of the chip. But ultimately, the bandwidth one can get out of a single piece of silicon is limited by the number of I/O pins multiplied by the speed per I/O pin, and it's independent of how many transistors are on this chip. So there's basically a bottleneck around I/O. And to clarify this a little more, the high-speed I/O known as SerDes, which is the serializer high-speed I/O, back in 2002, they were 3 gigabits, let's say. In 2006, it was 6.5 gigabits. Current chips have 12.5 gigabits, and the ones in 2014 will have 25 gigabits. So there has been progress, but it's only about double every 4 years, which is half the speed of Moore's law improvement. And on the packages per se, or how many SerDes people have managed to put on a chip, we had chips with 128 in 10 years ago, and now people are pushing maybe 200. So there's been some progress, but it's very, very modest. As a result, the maximum throughput per device, this is again a single chip thing, and big switches have many of these chips, but on a single chip basis, it really only has been a factor of 10x in 12 years, which is kind of consistent with the improvement in Ethernet performance from gigabit to 10 gigabit. But there is one other problem here, which is the way most networking chips have been designed in the past is the so-called ASIC flow. ASIC stands for Application-Specific Integrated Circuit, which means that the system vendor designs in Verilog the high-level logic, and then throws this netlist over the fence to the ASIC chip vendor, who actually then does the physical routing and placement on the chip and brings the chip back to the system vendor. Well, the problem with that design flow is you don't get to high clock rates because the high-level design is done independently of the underlying chip topology. In contrast, the way Intel or other people make high-speed CPUs is they start with a floor plan, and with a clock target is sort of the first constraint, and the whole chip data path is laid out to fit that clock target. And this is essentially the only way you get to high clock rates. So the full custom chips achieve much higher throughput and clock rates than ASIC designs. And to illustrate this, this is a contemporary 64-port 10 gigabit single chip. You can see it's a very structured design, this big memory arrays for the packet buffers and layer 2, layer 3 tables. In fact, there's very random logic on these chips. Most of it is just memory. Now, we are shipping this chip today in a 1U box that has 64 10 gig ports. Now, the alternative to this is you design things with ASIC flow, and the current implementation there is roughly 8 10 gig ports per ASIC chip. So you can certainly build a system that has 64 ports. You would need 8 of those 8-port chips and another 2 for the crossbar to tie it all together. So it would be a total of 10 chips instead of 1 chip. Same function, it's just a lot more chips. Now, there is no real advantage to the ASIC flow because the custom chip is denser, lower latency, fewer chip crossing, less power, more reliable. But the bottom line is the ASIC flow is simply not keeping up with Moore's law, and this is one of the explanations why the cost performance of traditional switches and routers just hasn't kept up with what is actually possible in the silicon side. Now, to give you a preview or sort of an outlook here, what we would expect to happen next year. So the chip that we're shipping today, the one we started shipping today 3-4 years ago, was a 24-port chip in 130 nanometer technology, doing 360 million packets per second, 2 megabyte buffer. The current version is 65 nanometer, almost 3 times the throughput, quadruple the buffer size, quadruple the table size. So big progress there. The next chip coming out next year will double that again to 128 ports, 2 billion packets, 60 megabyte buffer, double the tables, etc. And the one after that, we would expect to double again to 256 ports on the 10 gig ports on a single chip, 4 billion packets, double the private buffer, double the tables. So at least for the next sort of 2 generations, we actually do expect the silicon to be fully on Moore's law. And part of this is that the industry hasn't really caught up on the silicon roadmap. In other words, Intel is designing 22 nanometer CPUs today, whereas the current shipping silicon is actually 65 nanometer. So there's a big gap between the processes that are used in networking chips and the ones that are used for state-of-the-art CPUs. But needless to say, the cost performance of these systems should also improve at the same rate as the silicon content. So we do expect a very rapid improvement in cost performance as well. And this is the same chart here emphasizing, how many transistors are on these different technologies, the throughput achieved from these technologies, and bottom line here, even though the I/O does not scale as well as Moore's law, the combination of improvement in the process roadmap and really taking advantage of what the silicon is capable of doing by doing full custom designs will actually get us back to a point where the chips do what silicon enables them to do. Now, what this means on the system side is that servers themselves have, of course, improved greatly, and this is a chart courtesy of Intel Corporation that predicts the acceptance or the adoption of different networking speeds at the server interface level. So as of the last 10 years, in yellow here, everything was gig connected. The orange coming in is the 10 gigabit, and then the blue coming in a couple of years should be the 40 gigabit interfaces, and the green at the very end is the 100 gigabit Ethernet. So even though nothing has changed in the last 10 years, in other words, it took 10 years to get from gigabit to 10 gigabit, we would expect that in as little as 4 years, people will actually upgrade to 40 gigabit Ethernet ports on their servers, and 4 years after that to use 100 gigabit. And this is leading to all kinds of forecasts from the market researchers of what this means in terms of data center spending. This is a slide from a company called Crehan Research that follows just the data center market. So this is only data center, not other Ethernet markets. And in the data center, even as of this year, the vast majority of network spend is in fact 10 gigabit connections, with 40 gigabit coming in on the top and 100 gigabit expected to show up in, say, 2015. So again, the bulk of future spending is believed to be the 10, 40, and eventually the 100 gigabit. And what's driving this is, of course, the faster CPUs. The Sandy Bridge, which is the current Intel generation, in many cases has 10 gig NICs on the motherboard. In some cases, people have to add a PHY adapter to choose between the SFP and the 10 gig BST port. But based on the ever-increasing speed of these CPUs, it's basically believed that by 2015, most servers will be 10 gig connected, and that the market for these switches will grow very rapidly from 5 million ports in 2010 to over 60 million ports in 2016. Now, part of this is that a lot of the new designs are clusters or pods that connect servers into larger arrangements for Hadoop, Big Search, all kinds of applications. And these clusters are also getting bigger and bigger, and we'll talk about that next. So the second part of my talk here is what's really happening in the cloud and these large data centers people are building to deliver cloud services to consumers. And I'll use two examples here. One is our Arista 7050 racktop switch. This is the one with the 64-port single silicon doing 1.28 terabits throughput at a typical power of 2 watts per port. And the second one is our modular chassis switch, which is 384 ports, 10 gig non-blocking with a 10 terabit fabric. Now there's two ways to scale networks easily. One is at layer 2 with MLAG, which is our word for multi-chassis lag. We essentially take 2 of the 7500 switches and make them a Siamese twin, so they behave like a single 802.1 D bridge for forwarding, but they're really 2 separate switches. If one fails, the other one takes over. And that works well for small clusters up to the equivalent of 2 of these big switches. The other one is at layer 3 using equal cost multipath load balancing on top of BGP. So the layer 2 design is quite popular for building Hadoop clusters that are a couple of racks, or other things where people want a flat layer 2 kind of network. And this works today, no proprietary fabric required here, and gets people about 20 terabits of throughput for the size of these clusters, which could scale up to hundreds and hundreds of racks, but typically is a handful of racks. The layer 3 design is much more scalable because there's no layer 2 limitation, of course, and we have customers that have deployed this with up to 16-way ECMP, delivering 320 terabits full duplex over a large number of servers. And again, no proprietary fabrics here. In fact, this is a better representation of what it looks like. So the number of servers, or let me say this the other way around. So the spine layer, which is the big switches on top, basically determine the aggregate throughput of the entire cluster. And the bandwidth per server is how many servers are connected to that spine layer. And that depends on the application requirements and how much bandwidth is required. So people do either 1-to-1 non-oversubscribed or up to 10-to-1 oversubscribed, depending on the application. But the simple design guide is you start with the requirement on the pod size and the bandwidth per server, which determines the total cluster bandwidth, and then you select the degree of ECMP redundancy required, anywhere from 4 to 32 way, and that determines the bandwidth per spine switch, and then you connect it all together, and that actually is the cluster. So People are very careful to optimize this for overall cost per bandwidth per server, but this is how some of the largest websites out there have been built. The current topic, of course, is when does it make sense to go from 10 gigabit to 40 gigabit to 100 gigabit? And one important notion here is the notion of cost performance at the bandwidth level, which otherwise one can think of as a utility function. And one of the challenges is that 40 and 100 gigabit today cost more than the corresponding number of 10 gig ports. So our largest customers are looking at this saying, well, until 40 gigabit or 100 gigabit is actually cheaper than the equivalent of 10 gig ports, it doesn't make a lot of sense to deploy it. And this is a little bit unfortunate in the sense that the IEEE standards were completed years ago. So the 40 gig and 100 gig standards were done in 2007, I believe. But as of today, the cost per port is still higher than the equivalent number of 10 gig ports. The 40 gigs is actually getting there, but in the case of 100 gigabit, it's vastly more expensive. And the real issue is actually the optics cost, which is certainly 100 gigabit optics are extremely expensive, and 40 gigabit optics are still more than four times the cost of a 10 gigabit thing. So what I want to talk about next is what's going to happen on these optics. And again, the typical leaf spine cluster configuration is that within the rack, people use Twinix copper cables to connect from the server to the rack. There's no optics there. But to get from that leaf switch to the spine switch, depending on the size of the cluster, is either 100 meter or could be a 300 meter reach. And in some cases even longer. So as people in the 10 gigabit world, there's relatively low cost optics to do this, but for 40 and 100 gigabit, the optics that are currently the IEEE standards are the so-called LR4 optics, which are quite a bit expensive. And the key is to minimize the total solution cost, which is the combination of switch port, laser, fiber, and even power consumption. So a little history here. On the 10 gig side today, most people use SFPs, which support both the Twinix copper cable and literally any kind of optics, including dense WDM lasers that one can plug in there. The only other standard is, in fact, the RJ45 plug for 10 gig BST. This hasn't been very popular yet because it's a higher power consumption, but maybe it will still take off in the future. But again, most people, they use just SFP. Now, if you recall, it took a 10-year struggle for 10 gig to get here. The industry started with XenPack, which were these huge, bulky modules in 1999 or 2001, I guess. Then there was XPack, X2, XFP, and finally the SFP. And it didn't really help adoption of 10 gig that it took so many form factors. Now for 40 gig, luckily, there's only one known standard, which is QSFP. This was driven initially by InfiniBand, which is a 4X kind of technology and is the form factor of choice for 40 gigabit. Again, this supports both Twinix copper cable up to a few meters and various types of lasers. The two lasers out today is the LR4, which is a CWM that goes up to 10 kilometers, and the SR4, which goes 100 meters. And then for 100 gigabit, we have a similar picture as for 10 gigabit 10 years ago. There's currently CFPs, which are very big modules. You can only get 4 across a 19-inch panel. CFP2, which hasn't shipped yet, which is supposed to be twice as dense. CFP4, which hasn't shipped yet either, 4 times denser. CXP, which is a high-density copper connector, and some people just want to go straight to QSFP, which has a lower power capability, but is obviously much denser. But there is a lot of choices here, and the current ones are not very desirable. But there is an optical problem here, which is as follows. In the 10 gigabit world, the 10 gig SR running at 10 gigabit was actually able to go 300 meters with OM4 multimode fiber. And then beyond that, there was LR, which can go, say, 10 kilometers, and beyond that, there's ER going to 40. Well, with 100 gigabit, the SR4, which is the one uses 4 times 25 gigabits per channel, only will go 100 meters, maybe a few more, but it's basically a 100-meter technology. And the only other thing is LR4, which is a rather expensive technology and not cost effective. So for the large cloud data centers, people really need something that can go to 300 meters and in some cases 1 kilometer. And there isn't a known standard at the IEEE that actually does this. Now, there have been quite a few meetings about this, and quite frankly, what helped the most was certain end customers showing up at the meeting saying, we need a solution here. There was a presentation from Microsoft at the last IEEE meeting that said, you know, we just got to have this because this is the most important distance requirement. And this is actually finally getting some attention. So let me skip forward here. So there is a new technology known as silicon photonics, which is building the modulators right on the silicon chip and then having a single laser that gets modulated with the silicon. This is just starting to ship. People spent the last 10 years researching this and getting this into production. But it has the attribute that it has both the lowest sort of laser cost, the lowest silicon cost, the lowest fiber cost, and also the lowest power. So this is actually a very attractive technology, even though it's not in the current IEEE standards. And it has the promise of both very high density, meaning 48 ports, 100 gig per 1U, as well as the opportunity to get up to 1 kilometer in the same technology. And this will use parallel fiber. So I think you're familiar with parallel fiber, which is you put multiple fibers into a single jacket. This can be done with 8 fibers, 12 fibers. We actually like the 24 fiber, which is more cost effective than the smaller fiber count on a per fiber basis. And these parallel fibers are very dense, meaning one of these cables is no thicker than a Cat5 cable, even though it has 12 duplex channels. These parallel fibers are terminated with the so-called MPO, MTP type of connectors, which were invented by NTT in Japan in the mid-1980s for telecom initially. But this is the standard connector for multi-fiber termination and is now used primarily in data centers. And the standard connector has 12 fibers per row, 24 per 2 row, etc. Again, we like the one that has the 2 rows because it's more cost effective than the single row. So one of these plugs can handle either 12 10 gigabit channels or 3 40s at 10 gigabit speed or 300s at 25 gig speeds per channel. And they actually made it into the data center cabling standard in Europe known as EN 50173-5. Which lists both the LC connector, which is the duplex connector for the equipment termination, and then the MPO for the parallel fiber structured cabling between the racks, which is what most people do. And there's the equivalent in the TIA standards. They use different verbiage, but it's essentially the same concept. So the crucial thing here is that parallel fiber, in particular parallel single mode fiber, is vastly cheaper than traditional duplex multimode fiber. These customers are large quantity, like 100 kilometer spool kind of numbers, so basically you buy it wholesale from the fiber manufacturer, and I normalize them down to 8 fibers and 2 fibers for 300 meter or 1,000 foot distance. Now, what people do today typically, which is 2 fiber OM4, is roughly almost 5.5 times more expensive than the same fiber cost at a multi-fiber, 24 fiber, single mode fiber. And, we don't know all the reasons why the gap is so large, but it is clear that if you want to save money in a data center, you actually would want to deploy just parallel single mode fiber. On the other hand, there is today no low-cost optics for single mode. Remember, all the SR lasers, which are the cheapest ones, launch into multi-mode, not single mode. So there's this very unfortunate situation that basically all data centers have been cabled up with multi-mode historically because it was the cheapest optics. But to actually get to the cheapest cabling and the cheapest optics in the future, we'll need single mode, and it's just the way it is. So think of it as good news, bad news. It will work up to 100 meters in the existing cables, but if you want multi-100 meters distances or cheaper overall cabling, you will have to convert. The overall total here, it's a little hard to say because the silicon photonics haven't shipped yet. It's generally predicted that they are less expensive than even the VCSELs that are shipping today. And in the combination with the Pearl mode fiber and the lower power, it will be the lowest cost solution. Unfortunately, at the IEEE meetings, nobody's really allowed to talk about costs because that would be anti-competitive or antitrust, I don't know what. But from a technology side, it's pretty obvious what's happening here. Now, to sum this up, basically, silicon photonics is a good thing. It will vastly reduce the cost of high-speed optics for data centers while improving power consumption and reliability, and it can support kilometers of reach. Pearl single-mode fiber is a good thing. It's vastly cheaper than multimode. Unfortunately, again, most installed base is the multimode fiber. And having fewer connections is a good thing too, because it's much less confusing than what's going on today, where I didn't want to show pictures here, but you have seen the morass of cables that result in a large data center. But to sum this up here, over the next couple of years, we do expect very rapid improvements in cost performance for data center switching, basically being back on Moore's law, double the performance every other year. We do see rapid adoption of 40 gig and 100 gigabit once the optics costs are in line, and this should happen over the next 2 years as well. And again, the silicon photonics with the Pearl single-mode fiber looks like the most promising way of actually solving that problem and is a lot less cables and connectors. So these are all the slides I have. I thank you for your attention, but I think we have a little time for some questions, maybe. Thanks.
Hi, Bill Norton, and NANOG member. Thanks for the presentation. That was awesome. Could you say a little bit about the growth of power draw on a per U basis over time?
Yeah, that's a very good topic, and first of all, the ability to cool things tends to vary depending on the data center design. So data centers that were designed for higher power consumption, in particular high-density server racks, can obviously take a higher power consumption than some of the traditional telco data centers that had a much lower power envelope to begin with. But what is happening is that it's basically cheaper to put more chips on a single board and sort of increasing the power per 1U than building bigger boxes that distribute the chips more and have essentially less power per 1U. So the maximum power consumptions people are targeting per rack in high-density data centers tend to be around 10, 12 kilowatts in a typical data center. In high-performance computing, it's more like 20 to 30. But on a 10 kilowatt rack, if you have 40U, you really don't want more than 250 watts per 1U. So at our company, we're designing our switches to fit that envelope, which is to be essentially less than 250 watts per 1U, in some cases significantly less. So the switches are no worse than the servers, but the total, if you fill up a rack with these kind of switches, it would still be more than a traditional telco power envelope has been designed for. I hope that answers the question.
Todd?
Todd Underwood, Google. So earlier in the talk, you gave this fascinating comparison between ASIC design and custom chip design. And the implication of the discussion, as I heard it, was the many, many years of ASIC design was just a horrible mistake that was made over the course of a very long period of time. But you didn't imply that there was any good reason that anyone did this. Can you comment on why it was such a long-lived mistake in chip and system design?
Yeah, that's a very good point. ASIC design is much cheaper than full custom. So in ASIC world, I don't know if I have absolute numbers here, but it's probably a quarter of the cost and effort compared to do a full custom chip. And part of this is how many chips are you ever going to make? How many chips are you going to sell? So full custom has been applied to the higher volume opportunities, and if a router has so many chips but the company only sells so many routers, you can't actually quite justify it. So this is a trade-off in design cost versus optimizing on the silicon side. But as 10 gigabit volumes in particular, and Ethernet has been the highest volume thing in the market, What the industry has done and all the vendors are doing is to switch over to the full custom design to really deliver the optimal performance for that. So this is a little harder on the traditional, exotic kind of or lower volume kind of things, because people are not generally doing full custom chips for those type of devices. So it really benefits the higher volume Ethernet more than the traditional routing, which is also why I think we're not going to see quite the same progress there in terms of cost performance as we're going to see in the 10 gig, 40 gig, 100 gig Ethernet space.
Thank you.
Hi, Avi Friedman with Server Central. I had come up to give you a little bit of a sort of small and mid-sized provider view for people that are doing cloud-type applications, data centers, cross-connects in the 10 to 100,000 square foot space where discrete clusters are in the range of tens to hundreds of nodes. For a number of years now, gig and 10 gig connectivity, the actual optics and fiber, have actually been almost identical in pricing. Now, not if you look at Cisco, or I'm not familiar with Arista list pricing for the actual optics, but if you actually look at buying in big volume, it's a $50 or $100 difference per optic on top of a $200 optic. So you'll be doing copper locally for the massive servers, and then at the top of a cabinet, a lot of people already have deployed single mode because at that kind of cost delta, it didn't make sense to optimize, and you could then do your bigger, your larger clusters. Now, my friend VJ tells me that I failed to understand scale, and that is my problem, which has been the case for probably 10 or 15 years, and that at really large scale that Google and Microsoft face, that dollar difference does make a large difference, and the problem that you're describing, is big. But I've seen in a lot of what I would call the larger than hoster, but the commercial cloud space, a lot of people have already gone single mode because the cost difference has not been that much. Now, I expect the first couple years of 100 gig with the optics that you describe, it would be a monstrous cost difference, and people would be looking at single mode, but at multi-mode. So just point of information.
Yeah, and it is a good point. If you really have single mode, you are in fact way ahead. Even on the 10 gig side, the current standard, which is 10 gig LR, is a little bit more expensive than perhaps it should have been for a data center application, because it was designed for the 10 kilometer distance. We will launch shortly a thing called LRL, which is LR light over single mode, which is like half the cost to get to 2 kilometers, which would have been just fine for data centers. So even in that space, people are still cost optimizing. What I was really talking about is on the 100 gig side, the current LR4, which is a CFP module, even if you buy it at wholesale costs, let's just say 100 times more than an equivalent 10 gig module, and it's just from a cost per bit standpoint, not cost effective, apples to apples. So those kind of 100 gig lasers have to come down an order of magnitude in cost, even at the component level, before anybody should deploy them in any kind of volume. And that's what silicon photonics will do. So the initial silicon photonics sense will be cost competitive compared to a 10 gig cost, apples to apples.
And when will those be available commercially?
2014.
Thank you.
Martin?
Martin Levy, Hurricane Electric. Other side. That's okay. Focus on the networking side. You basically assumed Ethernet. There wasn't a discussion as to whether it was anything but Ethernet. And I just want to throw the question out to you. We've got to this point in the industry where by default, everything is Ethernet. We don't discuss any other sort of interconnect for this type of work. Is that really where we've ended up by default, 30 plus years after Ethernet sort of started to get a standard?
Yeah, I'm not sure it's the default in the sense that it's simply the volume standard. I mean, you can still buy SONET interfaces at exorbitant costs from various vendors, but it just isn't cost effective. So at the end of the day, most traffic is packet-based, and it works best over this kind of common Ethernet infrastructure. And this is even playing out now in the wider networks. And the whole SONET versus Ethernet wars are basically over.
Okay, so some people know my follow-up question. Are we really going to continue to live in a 1500 byte world?
Now that limit has been removed years ago, so you can do jumbo frames, 9 kilobytes on most people's equipment, including ours.
Can I quote you on that one? Sorry, that was a cheat on my side, but thank you.
We're going to add don't feed the troll to the rules of decorum on the mics. Any other questions? I see we have one.
Vijay Gill, Microsoft. So one of the things that I saw when you were showing the silicon roadmap in terms of speeds and feeds is that the buffer sizing seemed to be constant. Where you're doubling the ports, the buffer size goes 2x. So buffer per port seems to be flat. Now, in some of our experiments in previous lives, turns out that buffering is not as big of an issue, but with jumbo frames, I don't have a good handle because we've never tried that with the same buffer size. So any comments on whether we should be increasing buffer, decreasing buffer, or just the ratio of buffer to port seems to be okay for now?
Yeah, so this is actually a very important topic, and I apologize I glossed over this, which is for the single chip designs, where the entire switch is on one die. There's a very tight constraint in terms of die area. How many SRAM bits can you put on this die? And 16 megabytes is 128 megabits. These are SRAM cells, so there's actually almost a billion transistors just for that SRAM buffer, and then the other logic, right? So that's stretching the single chip designs. And if you then build a class networks out of these individual chips, it's still the same buffer overall. There's another type of chip design that uses external DRAM for buffering, in which case the buffer is essentially infinite compared to the single chip. And this is what we use on the modular chassis, where it's at least 50, if not 100 milliseconds worth of buffering per port, similar to what traditional routers have done. Now the trade-off is that those chips need like half the pins to hook up to the DRAM, and they don't get the same port density to the front-facing port, and then they're typically fabric interfaces. So the number of ports for the chips that support the external DRAM buffer is much lower than the single chip designs, and as a result those systems tend to be more expensive on a per port basis. But they are very popular for the core switches or the spine layers, where people don't want to worry about packet losses and the unpredictability of performance as seen by the end application that happens if various flows get dropped. So what this all comes down to is, for the most predictable performance, you don't want to drop packets at the spine layer, and you actually want the big buffers. But if the network is more resilient, in terms of performance requirements, even the single chip designs that have the smaller buffers may work. But it may depend on your application, and also depend on of all things, the TCP stack that you use. In other words, the real problem with packet drop is that the slow start recovery time puts an enormous performance burden on that application, and perhaps if the TCP stack was different, that may not be the same effect, but at least in the general world, the TCP stack is what it is. But this is something that perhaps could be changed. So the best way to think about buffers is that at the leaf layer, you can use 803.6 flow control and just admission control to not overrun the buffers at the leaf switch on a point-to-point link. But at the spine layer, because you have aggregated flows and aggregated traffic, you don't want to use flow control in that sense, and you will have to live with the effect of drop packets, and that effect depends on your application. It's a long answer, but
no, that's exactly what I was looking for, because one of the things we've noticed talking with application developers is, depending on the application type, and they're more interested in what is like the 99th percentile response time rather than having the buffers delay, because variance is what kills their workload, right? So in this case, then small buffers and no oversub is actually better for some workloads than actually putting in external buffers, which of course drive chip and power cost. Thanks.
Yep.
This is not height compatible. Thanks, Dave. Tony Capello, 5.9's excellent presentation. I want to kind of highlight or dive in a little bit on some of the slides that you had, which were talking about allocation of various things on the die. Seems like a very critical decision to make, depending on what kind of outcome one wishes. Something I'm not sure it was your responsibility, but somehow the Catalyst 4000s have this very nice feature for managing the use of the buffer memory, DVL, which allocated some number of bits per flow hash, and collisions were limited, provided some decent fairness to a rather small amount of memory per port, or per chassis, I guess in this case it was centrally switched. So I like that concept. I haven't seen that concept anywhere else. What do you think about that?
Yeah, I was actually the co-inventor on this particular idea, and at the time, this was 1998, so a long time ago. The whole rage was RED, which stood for Random Early Drop, right? So the notion was, if one drops packets randomly, that may be better than overrunning the buffers and dropping a whole bunch at once. So people at Cisco at the time implemented RED in various switches, only to find out that when you turn on RED, you would never hit the Ixchor performance test without dropping packets, because you would always drop packets by definition, right? This is what RED does. So as soon as that became clear, everybody turned off RED because it wouldn't look good on the performance tests. And the essential problem was that it isn't actually the mix of TCP flows, but what we then called ill-behaved flows. Basically, if somebody just injects this UDP, either unicast or multicast, it never stops, right? Which then consumes all buffers because it just takes over the switch, then it penalizes all the other things that may be going on. And the fairest thing to do would be simply look on a per flow basis of allocating, spreading out this, this valuable buffer memory on a more equal dynamic basis to the flows that actually want to use it, so that no flow gets too much and too little. And that was the notion of dynamic buffer limiting. And that worked really well. In fact, that particular product was one of the best-selling products in the cloud space, and part of this was its performance characteristics, and people never had an issue with buffer on that particular product. But that product still had vastly more buffer than the single chip designs today. So the buffer amount on a Catalyst 4948 is about 50 milliseconds per GIGI port, compared to the single chip designs, which have basically one TCP window per port, which is nothing, right? So the buffers on the single chip designs are in fact very, very small, and at the moment they get overrun, things will drop. And the only way around this is to use access submission flow control at the leaf layer, which people use, and that works reasonably well. But at the spine layer, it's much more touchy.
So would your point be, I guess, your assertion be that they're so small to begin with, any additional slight changes or fixes such as DBL or things like it really wouldn't be of any net benefit?
No. So what happens today is the big buffer designs use DRAM and just vast amount of DRAMs to over-provision buffering. The small ones are so small that you couldn't actually allocate the buffer on a per flow basis because there's not enough buffers on these flows. So it would work with a medium-sized buffer, but that doesn't fit on a single chip today, so it's not being used today. I think we are running out of time here, right? Or last?
We're done.
We're done. Okay, thank you very much.
Thank you.